Okay, let's look at this one with the Newman diagrams. First thing I'm going to do is I'm going to redraw these, not as Newman diagrams, alright? So in both cases, I'm going to be looking from the right side of the molecule, okay? Which means this carbon, I'm going to label blue real quick, and then I'll have the ring be green. So in both cases, the blue carbon is going to be on our left, and the green ones will be on the right. Alright, so there's the bond that we're looking down for the Newman diagrams. Okay, let's start on this one. On the blue carbon, we've got a methyl group going up, a chlorine coming towards us, that's going to be a wedge, and a hydrogen going away. Okay, now we're looking at the carbon that's this circle in the back, that's the green one. The methyl group's going down when we're looking from over here, so we're looking from that way. The methyl group's going down, the hydrogen's coming towards us, and the chlorine's going back. So hopefully that's not a problem to do that, to draw that. Now let's do it over here. The blue carbon, methyl group's going up, hydrogen coming towards us, chlorine going away. On the back carbon, that's the green ring, the hydrogen's going down, the methyl group is coming towards us, and the chlorine's going back. Okay. So now that we've redrawn them, we can notice a few things. All right. In both cases, we've got the same formula, and everything's connected the same way. We've got really all it is a 4-carbon chain. That would be a butane with 2 chlorines on the 2 and 3 carbons. So it would be 2,3-dichlorobutane, and that's true over here as well. Okay, so they're not constitutional isomers. All right, back in last semester, you would have just called them the same thing. Okay, but we want to make sure, are they really the same thing, or are they some kind of enantiomer? All right, and the next thing I'm going to notice is we've got 2 stereocenters on both of them. Okay, and in both cases, each stereocenter has the same things bonded to it. There's a methyl hydrogen chlorine. Over on this side, there's a methyl hydrogen chlorine. So there's definitely a possibility that we have some plane of symmetry, which would make it a meso compound if there was a plane of symmetry. All right, so let's check that. How I like to do it is I like to make the carbon chain look like this. So I've rotated the right side, which means I'll just recopy this one as it is. But now I've rotated the methyl group up. Whenever I do that, now the chlorine has come around towards the front. It's going to be a wedge, and the hydrogen's the dash. Alright, so as soon as I do that, I can see pretty easily, okay, there is this plane of symmetry down there. So this is a meso compound right here. But I shouldn't right away select meso compounds. Do not do that. Why? Because just because this one's meso doesn't mean this is also a meso version. Alright, if it's a meso version, then they're both the same thing, and you would select meso compounds. But if this one's not meso, which is possible, then it will be the diastereomer of the first one. So we need to check to make sure this guy also has a plane of symmetry to see if it's meso. Okay, so let's do that. I'm gonna do it the same way as before. There's my methyl groups. I rotated them so it looks like that. This one didn't rotate. So there's my hydrogen, my chlorine. Okay, whenever I move this methyl group up, now the chlorine moved down, but it's still in the back. And the hydrogen moved towards us a little bit. It's going to be a wedge. Alright, so we can see there is still a plane of symmetry, so they're both meso compounds, which means they're both the same thing, though you wouldn't choose superimposable or conformational isomers, because since they are meso, the best answer is just meso compounds. Now, before I stop with this one, I want to prove to you why we could not just choose meso to begin with as soon as we figured out the first one. Alright, so say I had included the Newman diagram that looked like this. There's my methyl, chlorine, hydrogen, chlorine, methyl, hydrogen. Alright, so now let me draw this one. We're still looking from this direction. There's my carbon bond that I'm looking down. Methyl group's up, hydrogen's coming towards us, chlorine's in the back. On the back ring, the hydrogen's going down, the chlorine is coming towards us, the methyl group is going back. Alright, so I did that. Now what? Let's see, is this one meso? If it was, then it would be the same as these two, and I'd be good to go. But let's see what happens whenever I let's rotate around the bond. So this side stayed the same. Okay, I'm going to rotate so that the methyl group is up. So here's my two methyls. Whenever I do that, bringing the dash forward, the wedge goes down. So the chlorine's in the front, the hydrogen goes to the back. Alright, so is there a plane of symmetry? Is that a plane? No, because the chlorine's in the front on the right, this one's in the front, but it's in the back on the left side. Okay, so it's not a meso compound. Alright, which means if I given this one and this one to begin, not the middle one, they would not be the same. They would not both be meso. This one is a chiral compound. It has two stereocenters and it's chiral. This one has two stereocenters, but it's not chiral. That makes it meso. So this one and that one are diastereomers of each other. Just to be clear, they're not enantiomers because the enantiomer of a meso compound is really the same thing. That's the whole point. They're not chiral. Okay, so I know that the relationship between these two, that's a diastereomer. Whereas these two are meso compounds, which also means that these two are diastereomers, since, just to be very clear, two meso compounds are the same thing. Okay, so there's no difference between these two other than some kind of bond rotation.